Now, in a typical mechanical drawing, you'll find that you'll probably have the architect or the owner's name up in the top right, followed by the engineer, the person who designed the actual mechanical system. You'll have the project name and address. And over here could be some dates, milestone dates, like when it was submitted for plan check and permit, revisions, and then down in the right corner should be the drawing number. So often people use different nomenclatures for this, but M being for mechanical, P for plumbing, E for electrical, and so on. So over here you may find the engineer stamp. That is a registered professional engineer. And then along here you'll find usually column lines that match up with the architecturals. So this goes 1, 2, 2.4, 2.6, 3, 4, and 5. It's kind of like bingo. Then horizontally you have A, B, C, and D. So if someone was to reference C3, they wanted you to look at C3 to discuss something in that area, then you just find C, and where it intersects column 3, then the discussion is around this point. Same with any one of these. D1 would get you over here, and so it's just for quick reference to find a location on the drawing. Down here should be which floor you're on and the scale, and then of course the north arrow telling you which direction is north. In this case the top of the page is north. So symbols. Understanding HVAC symbols makes it possible to understand what the engineer is trying to represent in simple graphics. So supply air is represented by an X, return just by a simple slash, and exhaust, the slash plus a little leg to the right. Here's their duct representation. So we have supply, return, and exhaust. That's the typical three that you'll see often. And then their diffuser, air diffusers, supply air, return air, and exhaust. So you can see the supply always has an X, whether it's a duct or a air distribution. Same with the return, it's going to have one slash, whether it's a duct or a piece of air distribution. Exhaust has a slash like the return, but then it has a little extra leg on the ductwork and on the diffuser. Alright, so this is a typical VAV terminal. You can see that this represents a point of connection to where the new ties into the existing system. So this is a new 14-inch duct tying into existing supply air main. And then you have a new VAV box, and you can see it has a reheat coil, but the piping's not shown on this drawing. So there'll be a separate drawing that shows the piping, and then it shows new ductwork coming off. And volume dampers represented by a little slash with like a handle to adjust the volume. So every piece of air distribution, unless it's only one off the box, everything should have a volume damper. That way when they do an air balance, they have something to adjust with. This is the supply air grill, and as you can see there's an X on here. And return, there's your single slash indicating return. And of course it says here N meaning new, return grill 1. And then you can see this on the back here, this indicates it's got a boot, which is just a way to absorb some of the sound coming out of that room instead of just having a grill. So this is what's considered an attic return because it's not ducted all the way back to the air handler. So the air just comes into the attic space and makes its way back to the main return air opening. A thermostat on here on the column on the wall, these are the windows. Controls that VAV box. Now symbols are not always shown correctly, which I'll show you on this. Maybe you can pick it out right away, but this is an exhaust fan. This is a plan view, meaning you're looking from overhead, you're looking down on it. and it's sitting on a equipment platform on the roof most likely. And this is the correct symbol. As you can see, the single slash plus one little leg, that's your exhaust. So that's the correct symbol for the exhaust. Now notice the wrong symbol for the exhaust on the same system. What does this symbol represent? Supply air. It's got an X. So in this case, the engineer made the mistake of showing the wrong representation. So they're not always correct. Engineers are human. They make mistakes too. Alright, so you can see this is a very congested area. Lots of ducts running through, lots of piping. These little single lines here, these are the pipes. The duct was drawn in double lines. So you can see this one here coming through. This is a supply, right? Supply shaft. This is exhaust, and there's your return. So these are ducts in a riser. There's a shaft right here. And so that duct comes out and makes its way to this heating coil, HC, heating coil. And then right at this point, we're going to try to determine what's going on here. So this is to help you understand hidden lines. So how do you know if a duct is going up or down? Which duct is at the higher elevation between these two? Now, to determine that, when these two cross, you can see that this one is on top because this line is gone. This is underneath. And the way you know that is you can see these lines are now dotted, which continues this piece. So the piece that has the dots on them is the piece that's underneath. So this represents this piece here. And this is on top, so you can see that blue piece here goes underneath. So you can see there's a line there where this upper piece sits on top that lower piece. So that line right there is right there where this blue piece came and turned. So there's that hidden line. So that tells us which duct is on top. So that hidden line belongs to this duct underneath, so he is underneath. This one's on top. What type of air is this? Supply, return, or exhaust? You can see the symbol there. That's a supply. So now elevation view, if you were to stand over here and look in this direction, this is what you would see. Now this is the same duct here, but this is plan view. This is when you're looking down on it, and this is when you're looking as if you cut a section through the building, through the duct, and now you're looking at it straight on. So here you are looking straight at it. So that blue piece is that bottom piece there. Is this bottom piece, and is this bottom piece on the plan view. And then the duct turns up, which is this riser coming up, and then it turns, goes this way, and turns and comes at you. That's what this is. This is coming at you. So that's that supply symbol showing now it's solid. That means it's coming at you, not away from you, as this is going down and up, but it's hidden because it's, if you're looking at a plan view, you're looking down from here. So that hidden line is right there. That's back here. So that's how you determine a hidden line. And that line there is solid because you can see that line. So this right here is all solid because you can see it. If you were looking down from here, you could see it, like here. You can see it. So that's how you tell a hidden line. So if he's looking down, if you're up there flying around, you can fly above like the wizard. You can see down. You would see a solid line there, just like you do there, just like you do here. But here you couldn't see this line in the back because you got this duct blocking your view. So to represent that hidden line, we make them dashed. So he's looking down, but he can't see through the metal, but this represents a supply. And so that's how you tell hidden lines. Now, plan view, this guy here, if you're able to fly around, just means a plan view means that you're looking down on it, as if you were floating above in a dream, floating above your bed or floating above the floor. You're looking down, so you can see the doors here, you can see the stairways going up and down, doors in and out. So that's the plan view, and this is the elevation. So really you have two types of views. You have the plan view where you're looking straight down on it, and then the elevation as if you took a knife and you cut the cake and you're looking on the insides of the cake. So as you can see, this is the second floor, and this duct is 4'3" from the floor to the bottom of the duct. And this is BOB, meaning bottom of beam, is 11'3" from the floor to the bottom of this big glue lamp. So this big wood beam here, it's 11'3" to the bottom. And here you are standing in there. So basically, this is a cut of the building. It's considered a section. So this is an elevation. This is a section view. Same thing.
And to understand and repair air conditioning electrical wiring and components, in reality, it's very easy. You'll find it's super simple. It's all really the same. If you know how to use a meter and trace out wiring, it'll be pretty simple. But all you need is an understanding of how parts work. So you have to know what the parts do and what they are, how they work, what makes them turn off and on in order for you to troubleshoot them. If you know what something does, then you can always see if it's doing it or not. It's very simple. You also need to know something's sequence of operation. And if you know those two things, you should be pretty good tech as far as understanding the electrical. And so, to understand how parts work, let's start here. We have, as you can see, a bunch of air conditioning parts, heating parts, and essentially wanted to talk about relays because these are pretty much all your air conditioning parts. Right here, outside of your big parts, which are your compressors and your motors, these are most of your little things. And I'm not going to cover every last single part in existence. We're going to cover the major, most common ones and help you understand electrical and how different parts are in reality the same thing. And so we'll talk about relays. Relays. These are all relays. That's all they are. Now, they open and close. Even this is essentially, well, it's a safety, but it works something like a relay. And I'll explain. And so, this is a contactor. This is a relay. But they both do the exact same thing. They open and they close. And so if you have power coming in to this from your breaker and it's open, your compressor and your contactor are all wired here, but as soon as this closes, power is bridged across and sending power to all of your parts. Therefore, closed means bridging power across. And so this and this do the same thing. You would have power going in, and this would go to your parts, whatever you had this wired off of. And these are both controlled. What differentiates these type of relays is what tells them to open or close. So this contactor is told to open by getting a signal of 24 volts to the coil here, which will then close the contactor, sending power to your components. The relay would in fact do the exact same thing. If you read it here, you could see that the coil is 1 and 3 here and here, and so if you were to give 24 volts to this coil, and you had power here, it's normally open, and so this terminal and this terminal are normally open, meaning they're not connected with continuity. But if you give this 24 volts, they become normally closed, and so they connect, becoming normally closed, sending power through the other side, just like this. And so this is also a relay, just the same thing. It just looks a little different. They like to confuse you, but originally this is just another relay. So these here, just simply the very bottom two, A and B down here, are your coil, 24-volt coil. And just like this relay, this does the same thing, except this is just 3 different relays is all this is. You could put power here, 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 or here, and this is normally closed to there, and to there. So these are closed, these are closed, these are closed. But if you give it power, this will now de-energize here and switch up to here. Same with all 3, so you have 3 different circuits. So you just have to understand what a part is and what it does in order to troubleshoot. So here we have another relay. It just handles more duty, and that's the difference between these 3. Light duty, medium duty, heavy duty contactor. So the more amps you're going to be pulling, the heavier duty relay you're going to use. And so it's a contactor, it's a relay, but they do the same thing. Now here, we have a time delay relay. And so if you got power going in here, and you got, say, your blower motor coming off this way area, this terminal, and you energize 24 volts here, it's going to time delay, and so it's not going to come on for a few seconds. It's going to time delay before bringing it on. And so if you were to troubleshoot that, you would give it power, see if it closes after its time delay. Same here. We have another time delay relay, a double stack sequencer. And so you give 24 volts to the bottom here, and the disk starts warming, and after a second, this one will close to here, so that one will close to there, and then after another second, that one will close to there. Purpose would be, maybe you could send your, if you were working on a straight cool with strips unit, and you wanted the heat to come on, you would energize, you would send common to one side, and you have the energized from white, and you would send power here and here, and this one would then bring on your heat strips, and then this one would bring on your blower motor. So your heat strips would come on, and then just seconds later your blower motor would come on after giving them a chance to warm up. That's what that's generally used for. But so you got to just understand what parts are in order to fix them. This open and closes also. It's really anything ever does is open and closes. It's just some open and close due to getting voltage, like all these, and some, like this one, open and close due to temperature. And so when this senses that it's too hot, this will now open. So it's a safety switch, but in reality, it's just a relay that opens and closes from a different type of signal. It opens and closes due to heat. Here, we have another. This is a pressure switch, but it's just a relay, guys. It's just opens and closes, but this one opens and closes according to pressure. So just like the rest of them, it'll open and close. You know how to test this. You know how to test all these things, because all they do is open and close. You get a meter, you put it on continuity, see if they open and close, or you just get your meter on voltage, and you know, if you have your meter here, and you have voltage, and it doesn't have voltage here, then you know it's open. And if you suck on the tube here, I'm sure you heard that. I heard it close. I'm sure if I had a meter on there, it would have all of a sudden started beeping because I would have had continuity. Just closes from a different signal. Instead of voltage, it closes off pressure. And, you know, moving on, we have a emission module, or circuit boards would be the same thing, but these are just a series of relays. It's just on the board, a whole bunch of them. And so if you were to, for instance, give this thing power, GH, 24 volts, and you're essentially giving this thing power, and so it's going to respond to your 24 volts. You have to know its sequence of operation now, because I would know that it would start sparking, and then it would energize the pilot valve. You just have to know how something's going to work. Here we have a transformer.